intermolecular forces and solubility are some other factors that we need to look at when talking about solutions. Now, the question is, why doesn't oil and water mix? And that's what we're going to find out as we go through this information. I need you to remember that we talked about different types of bonding this year. We had ionic bonding, polar covalent, and non-polar covalent bonding. Now, when we're talking about the bonding within an atom, we're talking about intramolecular forces. So this water molecule here has a polar covalency. There's an attraction from the hydrogen to the oxygen. And those are inside the atom, the individual atom. Inside the molecule, from one atom to the other within the molecule of water. So that's intramolecular forces. Now, when I put a bunch of molecules together, there are always interactions between the separate molecules. So this alcohol and water will have an interaction, and the two waters will have an interaction. And we call those forces intermolecular forces because they're forces that happen between the molecules. So let's look at some types of intermolecular forces. We have 4 different classes of IMFs, and I have them numbered from the strongest to the weakest. So notice that they are not in numerical order, they are in strength order. So the strongest type of IMF is the ionic bonding that we've talked about earlier this year. Remember that it has an electronegativity difference equal to or greater than 1.7. And if you'll remember our electronegativity scale, ionic bonding was from 1.7 or above. Polar covalent bonds is actually our 3rd strongest type of IMF. And it's when we have a dipole-dipole, where the electronegativity is from 1.4 to 1.7. I think I said 1.4. From 0.4 to 1.7, within that range. Remember that most molecules that we looked at this year ended up being polar covalent. Now, hydrogen bonding falls within this polar covalent category, but it's special and it's stronger. It's 5 times stronger than a polar covalent bond of any other type. So hydrogen bonding is actually the 2nd strongest type of IMF that we can have. Now, a London force is actually present all the time. In all of these other bonds, there will be London forces present. It's the weakest type of force, though, so all these other forces will take precedence over it unless you're in this small category of non-polar covalent bonding where none of these other things apply. Then the London force will be important. And remember that non-polar covalent is a difference in electronegativity equal to or less than 0.4. And there it is on our scale. I want to talk to you in more detail about hydrogen bonds and London forces. Now, hydrogen bonding, sometimes called H bonds, occurs when nitrogen, oxygen, fluorine are bonded to hydrogen. So it's not every time you see hydrogen. So if I see carbon and hydrogen, I'm not going to have hydrogen bonds there. It's only when hydrogen is bonded with these 3 atoms. Now what happens is that the dipoles on the hydrogens within the molecule is so positive that it will attract the unshared pairs of electrons on the other molecules within the substance. So I have 3 water molecules here. Oxygen with its 2 pairs of unshared electrons and its 2 hydrogens that it's bonded to. Now, oxygen is very greedy in the electronegativity sense, and it wants to keep those electrons for itself, leaving the hydrogens very positive. And so we see the dipole positive here. Now, the oxygen then becomes dipole negative. And what we see happen when I have multiple molecules of water together is that the hydrogen that is dipole positive will attract to these unshared electrons that are on the oxygen and get that positive negative attraction stabilized. So that's what the special quality of water that makes it very stable. It has all of these hydrogen bonds as well as its intramolecular bonding of the polar covalent molecule. Now, when we look at London forces, we're talking about movement of the electrons. And those electrons are in constant motion. Remember that they travel at the speed of light, and they are never in the same place from one second to the next. So they're going to create temporary dipoles in the atoms as they move around. So in one instance, I could look at this molecule, and I could see that the atoms are evenly distributed. But in the very next instant, I might look at that molecule and see that all of the electrons are aligned on the same side. Well, in that instance, there is a temporary dipole that will occur, where all of the electrons have gathered will be a negative dipole, and the other side will be a positive. Now, the interesting thing is that once a London force occurs in one molecule, it can make the other molecules nearby become dipoles. So the molecule that's next to this one will have all of its electrons repelled away from this side and go to the opposite side to get away from those electrons, and then it will in turn induce a dipole in the molecule next to it. And so these London forces, although they're temporary in a non-polar covalent bond, they become very important for making the molecule stable, because there will be tiny intermolecular forces that happen from one dipole to the other within those molecules. Now, I'm sorry, not within, between the molecules. Now, a good way to remember this is I've always taken the word London and applied it to a bus trip. If I were able to take the entire class to London on a field trip, and we got one of the double-decker buses to travel through downtown London, somebody might be sitting on the left side of the bus and say, "Oh my goodness, I see so-and-so." And everybody in that bus is going to want to go to the left side of the bus to see what it is that the student called out about. And so for that one temporary moment in time, everybody on the bus is on one side. And it's temporary because as soon as you all do it, I'm going to say, get back to your seats. And so you will go back to your assigned seat. So this is a temporary occurrence that happens when all of the electrons happen to be arranged on one side. So that brings us to the question, why do water and oil not mix? Well, the answer is that the oil, which is nonpolar, is pushed away because the water is polar. And so those negative dipoles on the oxygens will be attracted to the positive dipoles on the hydrogens. And as they draw closer to each other, they will push the oil away from them. And so what you'll end up with is the oil will be all together and the water will be arranged together, and there will be sort of a boundary between them. Now, I could shake the oil and water up, or I could heat the oil and water up, and those two things could break these bonds enough to allow the oil to mix in with the water temporarily. But if I stopped shaking it, or if the temperature cooled, the oil and water would separate again.